of resistivity, what we learned last time. Number 3 is asking find the resistivity of is rho of blood flowing through the vein. There are a couple of information given there, okay. But before we do this, we need to learn one more concept. Some of you have already seen that concept when you did the lab. Some of you might not have seen this. So we'll come back to this in a second, number 3. So before that, let's talk about this relationship between current and potential difference. Okay. So we learned last time resistance of a material is represented by this kind of symbol. Okay. So this is the continuation from what we learned last time. This is resistance, or the object is called resistor. Resistor is the object that offers the resistance to the current. Okay. So you can think of this as this kind of like zigzag pipe. Okay. So think of this as water pipe connected to some water tank or something. Say here you have water tank. Okay. So that's the water pipe. Oops, so I connected it incorrectly. So this one connects to the bottom here. So what do you think? Will the water flow in this zigzag pipe if I have this kind of arrangement? Is it possible? You have this water tank on the bottom, and you have this pipe. The pipe is above the, imagine that the pipe is above the water tank. Will it flow on the water pipe? Will the water flow on the water pipe? No? Why no? Or what do you need? Yeah, exactly. You need some kind of pump, right? Some kind of device to pump the water. So you need water pump. Here you need some kind of water pump. And this water pump will pump this water in the system. In the same way, to get current in this circuit, you need some kind of pumping device. Okay, you can say charge pumping device. Here it's water pump, but we need a charge pump, and that charge pump is battery. Okay, what battery does is it pumps charge in the circuit. Okay, and so what the water pump does is it creates basically it creates two regions. Okay, so how it works is by creating two regions, by creating this part that has higher pressure and this part that has lower pressure. The reason the water didn't flow before we introduced this water pump is because the pressure was same on the two sides. Now when you have pump, it has vacuum system inside. So the vacuum generates lower pressure region here and higher pressure region here. And because of the change in the pressure, the rule of the mother nature is objects or things move from higher pressure to lower pressure. Okay, so the water from higher pressure will flow towards the lower pressure. In the same way, what this does is it creates pressure difference. Okay, but we don't say pressure in current or in circuit. Instead of saying pressure, we call it potential difference. So this creates, battery produces potential difference between this point and that point. Okay, so this will be at, if this is positive end, of the battery, and if this is the negative end of the battery, we have two ends of the battery, positive and negative. So the part that is connected to positive end will be at higher potential. It's similar to pressure, but we don't call that pressure. And this would be at lower potential. Now we have this potential difference, and because of the potential difference, now the current will flow through the resistor, okay, through the resistor as well as through all the parts. Not just through the resistor, the current flows through the wire and also flows to the battery. Okay, so the current also goes to the battery. So it circulates all around the circuit. Now, if we have this kind of like series circuit, everything is in series, then no matter where you measure the current, whether you measure the current here, or you measure the current here, or you measure the current here, everywhere you get the same current. Okay, the current is same in a series circuit. So now this is very intuitive. Okay, it's about just seeing the relationship between potential difference and current. So now think about this analogy again. So in this analogy, higher the pressure difference, more is the water flow, right? If you have a little bit of pumping, a little bit of pressure difference, there will be a little bit of water flow. But if you have a really high pressure difference, you will see the water flowing at higher rate. Okay, so in order to get faster flow of water, you need higher pressure difference, greater pressure difference. In the same way, to get more and more current, you need more and more pressure difference, or I should say potential difference. Okay, so in other words, greater the potential difference, more is the current. More is the current. Okay. In other words, the current flowing through this is directly proportional to the potential difference that you apply, and it's vice versa. Okay, so more current means greater potential difference, and greater potential difference means more current. So they are related to each other. So in the lab you saw you can measure potential difference and current by a meter, okay, some sensor. So here is our circuit. Now I will not write the actual battery, so instead of you writing actual battery, I will write this. So this is the battery, representation of battery. This longer line is positive and shorter one is negative. And like we talked last time, there are two types of current flow. One is negative flow, which is the actual one, but since we have been using for long time this conventional current, where we assume that there is flow of positive charge. Okay, so we always represent the flow in form of flow of positive charge, positive going from the positive of the battery towards the negative of the battery. So it starts from here and then rotates all around. So that's the flow of current. And this is again conventional current, not actual current, but it doesn't make any difference with our dealing with the circuits. Okay. So if you want to measure current, you measure the current along this path. Okay, so you insert your current meter along the path. So whether you put here or here or here, these are the meters. Okay, the device that you use to measure current is called ammeter. It measures amperes, so it's called ammeter. It measures current, and ammeters are placed in the path of the current. That's how you measure the current. Whereas potential difference is measured across the component. So let's say you want to measure what's the potential difference between this point and this point. Then you connect your device across that. Okay, so you connect your device, which is called voltmeter. It measures the voltage. So voltmeter measures the potential difference. Potential difference. So you see the distinction. Ammeter is placed in the path of the current, whereas voltmeter is placed across the component. If you want to measure here, then connect one end to this side and other end to this side, and that measures the difference in the potential. Okay. So what kind of relationship is between V and I? So let's say you have current of 1 amperes, and for 1 ampere current, let's say the potential difference here is, so when there is 1 ampere of current flowing, you measure the potential difference here, and let's say it's 1 volts. Okay, just assuming some number. If I double the current, then that will also double the potential difference here. So if I send 2 amperes now this will have 2 volts. Okay. If I triple the current, instead of 2A, if I send 3 amperes of current, the potential difference across here now would be 3 volts. Okay, 3 amperes will produce 3 volts, 4 amperes will produce 4 volts, and so on. So this kind of relationship is called linear relationship or direct relationship, or you can also say directly proportional, meaning if you double one, the other also doubles. If you triple one, the other one also triples. Okay, so linear relationship. And if you plot a graph for that, so that's what you will do in your lab. If you plot current versus, or potential difference versus current, then whenever you have a linear relationship, linear means it will now fit with a straight line. So if you draw a straight line, oops, see if I can draw a straight line. Okay, so that will be the best fit line for your potential difference versus current. Okay, so mathematically we write potential difference delta V is directly proportional to I. Okay, and what that means is, if you take the ratio of delta V over I, let's go to the table up here. So you take the ratio of delta V over I, no matter which data point you choose, you get the same value. So 1 volt over 1 ampere is 1, 2 volts over 2 ampere is 1, 3 volts over 3 ampere is 1, 5 volts, no, that's not 5, 4 volts, 4 volts over 4 ampere is 1. So this ratio is always constant. Okay, we can see that from this data, and that ratio is called resistance of this resistor. Okay, this is denoted by R, and R is basically the proportionality constant. This constant is called proportionality constant, Ri. So, delta V is basically I times current times resistance. This equation is called Ohm's law. For this whole chapter, we will be dealing with this Ohm's law. We will be using this formula a lot. So, delta V is measured in volts. The unit for delta V is volts, which is capital V. I is measured in, you guys remember what's the current measured in? Amps or amperes, yes, amperes or A, and R is in ohms, capital Greek letter omega. So, if you plot this, then this slope, this is a equation of straight line. So, y is equal to mb. So, y is that, sorry, y is mx. So, x is that. So, your slope will give you the resistance. So, this slope is the resistance. If you are doing analysis of the lab, you will need to find the slope to find the resistance. So, now let us look at the problem number 3 from worksheet. So, it says suppose a medical device attaches electrodes in 1.5 millimeter diameter vein at 2 points 5 centimeters apart. What is the blood's resistivity if 9 volt potential difference causes 230 microampere current through the blood in the vein? So, the question is, so in the medical procedure they connect 2 points of the vein, okay, with the electrodes, and these electrodes are connected to some kind of meter, okay, that measures the resistivity. This measures the resistivity. Or it does not directly measure resistivity, it measures the current and delta V. Okay. So, this device can measure current and delta V, and in order to measure this, you first need to apply some potential between the 2 points. So, you choose this point A and this point B in the vein. So, this is vein with the blood, and you first apply some potential across A and B. So, let us say delta V across A and B is applied, which is 9 volts. Okay. By applying 9 volts, you measure how much current flows through the blood. Okay. So, the current flowing through the blood I is found to be 230 microamperes. Micro means 10 to negative 6. And then you are applying delta V, which you can also measure with the meter, 9 volts. And the diameter of the vein is 1.5 millimeters, which is 1.5 times 10 to negative 3 meter, and the length of the vein that we are considering. So, this length across which we are measuring the potential, that L is 5 centimeters, which is 5 times 10 to negative 3, not negative 2, negative 2 meters. Okay, so that's the given information, and with that information we are asked to find rho. Rho is the resistivity of the blood, and sometimes we can use that to know whether your flow of the blood in the vein is normal or not. If you have some kind of condition, whether the flow is normal or not, by looking at that. Okay, so how do we do this kind of problem? So whenever you see the quantity that you are finding, let's think about what the formula is. Okay, so whenever you are solving problem, think about what you are trying to find. You are trying to find rho, and think about what formula can give you rho. We know only one formula that can give us rho, that is R is equal to rho L over A. That's the only formula we have. Okay, so that's the first step. So to find the rho, we need to rearrange this. Rho would be R A over L. So to find rho, we need R, we need A, and L. L is known, so that's L. A is the cross section area, so that's the cross section area of the vein, which is not given, but we have this diameter. Okay, diameter is given, and we know area is pi r squared. So in terms of diameter, r is half of the diameter, right? So d over 2. So pi r is d over 2 squared. Pi is 3.14. d is diameter is 1.55 times 10 to negative 3 meter, and then over 2 squared. So that gives us area. So now we have area as well as length. So we need to find r. So if we could find r, then we can find rho. So how do we find r? Now think about what formula you have for r. This is one formula that we have for r. We cannot use that because we are finding this. So this is not useful. We have another formula. We just derived that. Yes. So Ohm's law, delta V is equal to I times R. So R is delta V over I. So delta V is 9 volts, and I is small current, which is 230 times 10 to negative 6 amperes. So you do the math, that will give you resistance measured in ohms. So now you have everything in this formula. So rho, you have this R, okay. You have A, area is from here, and then you have L also given. So let's do the math and see what you get. Does anyone have answer for this? What's that? This one is 3.10 to negative or positive? Positive 4. Okay. So what's rho then? So I have 1.4, and unit for rho is, we have ohm, meter squared, and meter. So that's the units involved in this formula. You can cancel one of the m on the top and m on the bottom, so that gives us ohm meter. Okay, so 1.4 ohm meter. You got 1.56. Okay, yeah, it may be just because we are dealing with very small numbers, so you may get closer to 1.4. What other people got? Do you guys have answer? No? Still working? Huh? 1.5. Okay, so maybe it's 1.5. You also got 1.5? Okay, so maybe it's 1.5. Maybe I didn't do the math correctly, so I'll change it to 1.5. Okay, you can do that. So
that's also ohms?
Huh?
Ohm meter?
Yeah, ohm meter. Okay, so we saw the relationship between delta V and I, and that's the usual relationship. Okay, so usually in general you see the relationship between delta V and I to be linear, but that's not always the case. Okay, so whenever it's linear, the resistor or the component that satisfies this kind of relationship is called ohmic resistor. If the delta V and current in the resistor satisfies this kind of linear trend by increasing one, the other increases by same proportion, that's ohmic resistor. But in some resistors, some components, it may not be linear. So delta V and I may not be linear. It may be a little bit of curve like that. Okay, so in this case, the component is non-ohmic. It's called non-ohmic resistor. The example of non-ohmic resistors are the light bulb. Okay, the light bulb you use. So you have light bulb connected to a battery. You measure the current flowing through the light bulb and measure the potential difference across the light bulb. Then you will find this kind of relationship. Okay, non-ohmic relationship. So in non-ohmic resistor, you cannot use this. This cannot be used. You can use this Ohm's law only in this kind of relationship. In the normal resistors, that's true. So we won't be dealing with any component that is non-ohmic. So we don't have to worry about this. Okay. So we'll not worry about this. Semiconductors also are non-ohmic resistors, but we don't need to talk about semiconductors in this course. Okay, so you now know the function of resistors. Resistors control the current. So if you look at the circuits, you will see lots of resistors in the circuit. Okay, so let's see. So these are the resistors. Okay, different kinds of resistors, and they all follow Ohm's law. And if you see the circuit board, you will see lots of resistors in the circuit board. So here, that's the circuit board. You see there, the resistors are everywhere. So here they have multiple resistors. You have all these resistors. Okay, and these cylindrical ones, you see these ones, these are the capacitors. The function of capacitor is to store charge. We talked about that last time. We'll be talking more about capacitors after resistor. So capacitors store charge, and resistors, they control the current. Okay. So, in actual circuit you will find resistors connected in different ways, okay, and all those different ways can be broken down into two ways. They are series combination and parallel combination. So, you can have a combination of resistors in series connection, or you can say connection or combination, and parallel connection or combination. And then third type would be the mixed of these two. Okay. So, we will be talking about that mixed part later, but in general we have this series part, combination and parallel combination. So, series is you have a resistor, okay, that has the value of resistance R, let us call R1, and this is connected to another one in series like this. Okay. The end of this one connects to the end of that one, and then you connect this to this one. Okay, that is R3. So, this is a series combination. Parallel combination, you have a resistor like this, R1. Now, you connect this end to the other end of the other resistor, and then this part connects to the other part of the other resistor. Okay. And then you have this resistor, and then you can have multiple resistors like that. Okay. You can have more than 3. I just showed 3, but you can have more. And then you can connect this to some, because you want to pass current through this resistor, and we know to have a current in the resistors you need a battery. So, you can connect this to battery. Battery pumps the charge in the circuit. So, that is the positive side of the battery, that is the negative side of the battery. You can connect this to a battery, that is the positive side, that is the negative side. Okay. Again, you can have more than 3, I just showed 3 here. So, 2 things you need to remember here, very important things. Okay. So, I want you to remember those 2 things. So, they are, whenever you connect resistors in series, the current flowing through each of the resistors would be same. If current I flows through this, the same current would flow through this one also, same I through that one also. Okay. If you have 1 ampere of current flowing through this, you will have 1 ampere through that, 1 ampere through that. Okay. So, current is same everywhere. In the circuit, I will just write CKT for circuit. Whereas the potential difference that you apply, so you are applying potential difference of the battery. So, this battery has some potential difference, let us say it is 3 volts. This potential difference would be divided among the resistors. So, part of this 3 volt will go to this one, part of this will go to this one, and part goes to that one. Okay. It may be like, it may not exactly 1, but I can say 1 goes here, 1 goes here, and 1 goes here. So, you will have 1 plus 1 plus 1 is 3. Okay. So, this potential difference is divided among the resistors. So, potential difference of battery is divided. So, these are the 2 things you need to remember for the series combination. Now, for parallel combination, so this battery has potential difference, let us say delta V. For example, let us say 3 volts. Okay. It could be 5 volts, 7 volts, 10 volts, however many volts you want. Now, this potential difference would be same across all the resistors. Whenever you have the things are in parallel, they will always have same potential difference. Okay. So, the potential difference here across these two ends is 3 volts. That is the two ends of the battery. So, this is the one end of the battery and this is another end of the battery. So, that is 3 volts. That same 3 volt will also appear on these two ends. Okay. These two ends means across this resistor, and you will have same potential across these two ends also, same here also. So, you will have same delta V, same delta V, same delta V. Okay. So, I will just write delta V here. Delta V is potential difference is same across all the resistors. That is the first one. And the second one is, so the battery produces some current, or the main function of battery is to pump the current. So, it pumps the current. Let us say the battery pumps the current of I, it could be, let us say 3 amperes, maybe different value, but I am just supposing it is 3 amperes. So, this 3 amperes will be divided among these 3 branches. So, we have 3 branches. Part of this will go to this branch, part will go to this branch, and part will go to that branch. So, if it is 3, 1, it may be 1 here and 1 here and 1 here. Okay. So, they will add up to this total 3. So, current is divided among the parallel branches. So, we can write it in symbolic form. So, in this case I can write current I produced by the battery is equal to current through the first resistor, current through the second resistor, current through the third resistor. So, current is same everywhere, whereas delta V of the battery is divided among the individual resistors. So, delta V of the 1, delta V of 2, and delta V of 3. Whereas, in this case current produced by the battery is divided among the resistors. So, R I1 plus I2 plus I3. So, these are current through each of the resistors, whereas delta V produced by the battery would be same everywhere, delta V of 1, delta V of 2, delta V of 3. Okay. So, knowing that, you can now solve lots of problems. So, let us look at a problem. So, let us consider we have a circuit like this. So, now this is the third type of circuit, which is the combination of both series and parallel. Okay. So, this is combined circuit. So, this is 2 ohms, this is 2 ohms, this is 1 ohm, and this is, let us say 2 ohms, and the potential difference of the battery is 12 volts. So, find current through each of the resistors. So, we want to find current through this one, current to that one, current to that one. So, because it is the combination, so current won't be same everywhere. They will have different amounts of current flowing through them. So, we want to find that. The first thing we need to do here is simplify the circuit. So, turn this into the simplest form, first step. How we do that? So, combine these two into one. Okay. So, this is 1 ohm, that is 2 ohm. What I did here is I combined these two into one. So, how we do that? Whenever you have resistors in parallel, 2 or more resistors in parallel, let's say R1, R2, R3, you can turn that into a single resistor, which is R equivalent, by using this formula. So, 1 over R equivalent, which is the resistance of the single one, is equal to 1 over R1 plus 1 over R2 plus 1 over R3, okay, and so on. So, use that formula. So, here we want to turn these two into a single one. So, you need to use this formula. So, 1 over R equivalent, which is this one, 1 over R equivalent is equal to 1 over 2 ohms plus 1 over 2 ohms. Okay. Take the reciprocal of that, take the reciprocal of that and add them. That will give you 1 over R equivalent. This is 2, sorry. So, 1 over R equivalent, if you do the math, you get 1 ohms. Okay, you are adding half and half, so that is 1. Now, this is just 1 over R equivalent. That is not what we want. We want R equivalent. So, we need to take the reciprocal of this. If you take the reciprocal of that, reciprocal of 1 is 1 ohm. Okay, so that's so R equivalent is 1 ohm. Okay. And now this one, and this one, they are all in series. Okay, so let's now simplify this furthermore. We can replace all these three into by a single resistor because they are in series. So, this is combination of these three resistors, and when you are combining the resistors in series, the equivalent resistor is given by this formula. So, R1 plus R2 plus R3, just add the individual resistors. So, 1 ohm plus 1 ohm plus 1 ohm, that gives us 3 ohm. So, this is 3 ohm. Okay. So, we got the simplest circuit. Now, for the simplest circuit, now we can apply Ohm's law. So, Ohm's law is delta V is equal to I times R. Okay. We have delta V given 12 volts and we have R. So, we can find I in this circuit. Okay. I in this circuit is given by delta V over R, just rearranging the things. Delta V is 12, R is 3 ohms, that gives us 4 amperes. Okay. 12 over 3 is 4. So, the current flowing through this is 4 amperes. So, there is 4 amperes of current flowing through that. It is same everywhere because it is just a simple circuit. Oh, right, okay, my bad math, sorry for that. This is 4. Okay, sorry for that. So that should be 3. So that means this 3 amperes flowing through the circuit. Yeah. So when you add 1 1 1 1 2, that should be 4. Yes. Okay. Now you go backwards. Okay. So everything is now going backwards. Now, if you go one step backward, you see that this resistor is the combination of 3 resistors in series, this one, and this one. So whatever current is flowing through this combined resistor, which is 3 amperes here, the same current would appear on each of these resistors because they are in series. Okay, so if there is 3 amperes flowing through this combined one, you'll have 3 amperes here, 3 amperes here, and 3 amperes here, because we know current is same everywhere for a series resistors. So 3 ampere, 3 ampere, 3 ampere. Now again apply the amperes Ohm's law for each of the resistors. So find the delta V across this resistor. So here this delta V across this one is given by I times R. So I is 1 and I is 3 and R is 1. So delta V would be 3 times 1 is 3 volts. You do the same thing here. Delta V is I times R. I is 3, R is 1, so delta V is 3 volts. Here delta V I times R is 3 times 2 is 6 volts. Okay. So we got delta V for all these 3. Now you go further back, one step further back. Okay. So we got the current here. So the current through this one is 3 amperes. That's the answer. We got the current through this one. This is 3 amperes also. We got the answer. Now we need to find the current through each of these ones. Okay. So this one, this resistor, is the combination of these two in parallel. Okay. And we know that the potential difference across the parallel resistors is same. Okay. So because this is the combination of these two in parallel, that means potential difference across this one would also be the same for each of these ones. Okay. So you have 3 volts potential difference here, and this one is in parallel to this one and that one. So that means this one will have 3 volts and this one will also have 3 volts because they are in parallel again. Okay. Now use the Ohm's law again here. Ohm's law is I is equal to, so delta V is equal to IR. So I would be delta V over R. Delta V is 3, R is 2. So that means I here would be 1.5. So 1.5 amperes. Here also 3 over 2 is I, which is 1.5 amperes. Okay. So we got all the currents. So we'll continue this next time. I think we are out of time. We'll do a little bit more practice next time, and that will make the things more clear. But that's all for today.